Hi, and welcome to my lecture on climate change and economics. I will try to provide you in about 30 minutes with my own selected insights and a critical appraisal, and at the end with a few insights on how COVID-19 might affect the whole issue. Yeah, my name is Mathias Kirchner. You will get to know me quite well, as I'm one of the teachers and moderators of the AEMS this year. But this is part of a larger lecture I actually give at Boca every year. So I hope you're going to find it interesting. Yeah, this is the content of my lecture. I will start briefly by showing you why climate change matters for economics. Helga Kromp-Kolb will give you a much better and more in-depth lecture on the issues of climate change, but this is just to cover the basic ground more or less. And afterwards, I will really try to provide you with a quick introduction to what climate change economics is, why it has impact on real-world politics, what's not so good about it, and maybe some things that we can actually take away from it. Yeah, so climate change, why it matters for economics. This slide already indicates why it matters, because temperatures have been rising for quite some time now, and this show your stripes graph more or less depicts the change in temperatures from pre-industrial times until today, which is quite remarkable. So why does it matter? I provided with more or less 4 reasons. First one is it's man-made, so it's our creation, more or less. The physical basis was already there in the late 19th century by Swedish scientists, Arrhenius, who wrote about the greenhouse gas effect, which basically is a natural law. And then nowadays we really know that we can attribute almost 99% of global warming to anthropogenic, that means human-made forcings. So it's us, me, you, who more or less contributes to this increase since pre-industrial times. And then that's the issue that really makes it an issue. It's unprecedented. We have not observed such a drastic increase in such a short time in temperatures for at least the last 11,000 years. So we know that temperatures have been higher in the past, million years ago, but they never changed so rapidly in what we have observed so far. And that really puts a lot of pressure on Earth ecosystems and in the end, probably also our survival. And the issue is, if we don't stop emitting greenhouse gas emissions, it could get really hot. And these are basic predictions by the IPCC. These are different warming potential scenarios. And you can see that compared to pre-industrial times, those are the times before we started to really use fossil resources at larger scale, it can get really hot if we do not mitigate or combat climate change. And it's imperative to stay below 1.5 degrees or at least 2 degrees. Those are the Paris Agreement goals, because it would allow us to keep within a safe operating space. Because the Earth system itself, and Helge will talk about this in more detail, there are some tipping points that we have to be aware of, which will trigger positive feedback loops. That means it's an enhancing mechanism, and it kind of triggers an increase after increase after increase. The most famous one is, of course, methane trapped in the permafrost. And if that melts, methane is released, and that kind of again raises temperatures. But there are many more, and the trouble is they're all interconnected. And the more we know about tipping points, the lower we have to put the threshold levels. So that's really something we have to be aware of and really put on a risk approach when it comes to climate change. Yeah, and the last one is actually, it's the economy, stupid. It's basically economic activity fueled by fossil resources that have been more or less driving climate change in the last decades. And here you can see usually a decomposition of the effect. It's usually decomposed into population change, affluence, so that's GDP per capita and the greenhouse gas intensity of GDP. And you can see while we had technological improvements, so the greenhouse gas intensity per dollar GDP decreased, it could not compensate the increase in wealth and population increase. So we have seen a constant rise in greenhouse gas emissions over the last decades. Yeah, so it basically is an issue because it's unprecedented. It poses existential risks to humanity. So there really is reason to combat and mitigate climate change. So what is climate change economics? So within climate change economics, you can identify two main aspects. The first one is related to a very core question of economics, which relates to how resources can be best allocated. You can allocate resources to combat climate change, try to reduce greenhouse gas emissions, or you can also allocate resources to adapt to climate change. You will have to do both, of course, but knowing how much to allocate to which category, that's a challenge. And the other one is to know this, actually, you will also have to know what are the costs of climate change. So that's also a very essential question is, can you quantify and attribute costs of climate change to economic activities? And that's a question that's, as I will show, very difficult to answer. You may also distinguish between two main objectives. And this is a very simplified view of climate change economics. And of course, there's much more grayness within the whole discipline. But I think I just try to keep it as simple as possible here to provide a quick introduction. And from my point of view, you have two really main schools. And you have one that identifies policies that maximize social welfare. So that's normative welfare economics. So they really ask the question, what is the optimal amount of greenhouse gas emissions that provides the highest social welfare? And then you have those more technical economists that just say, okay, how can we reach a mitigation target at minimal costs? Assuming that, well, we have a target, it's politically agreed, and we just have to reach it, and we want to reach it with at least cost. So that usually asks which technology is the cheapest to be employed in mitigating climate change. And you have equivalent methods that fit those objectives, of course. So you have what's confusing, I think, the most lay people out there is they're titled the same. They're both called integrated assessment modeling. Because in itself, it's a very generic term. It just means that you have different models which you integrate and then you assess the impact of policies. So it could actually be anything, right? But it's a term that was first coined for cost-benefit analysis. So for those models that really try to maximize social welfare, these are usually top-down macroeconomic models. Famous ones are called DICE and RICE. They're actually used by the Environmental Protection Agency in the US. And the other ones are cost effectiveness analysis, which are bottom-up process-based sectoral integrated assessment models. And they are similar, but there are also very important differences. And I've tried to more or less highlight these differences in the next slide. This slide provides you with a basic schematic of how these integrated assessment models work. On the left side here, you have a top-down integrated model framework. It usually includes a macroeconomic model, which can simulate from top down, so at a very aggregate level, economic activities and interaction between different sectors. It accounts for the change, for the impact of temperature change on economic processes. It also provides data on emissions and optimal mitigation measures, but although, again, at a very aggregate level. And there's interaction, there's a feedback loop between the very simplified climate model, which basically reacts to changes in CO2 concentration, and the macroeconomic model. And in the end, what it does, it maximizes welfare, that's its objective function, and it determines an optimal emission and temperature point for humankind and society. And here on the left side, you have a bottom-up integrated assessment model. So there's a big difference is there's usually not a feedback loop between the sectoral models and the climate model. So you usually run specific emission scenarios by global circulation models. So they assume certain pathways for concentrations. So it's called representative concentration pathways. What you have exogenous input on climate policies and emission targets, and you usually try to meet the emission targets, which are usually disaggregated to the sectoral level, land use or energy. And what's also similar between macroeconomic models and bottom-up models is that you have some exogenous assumptions on population, technological development, and so on. And what these models usually do, they usually also integrate weather data. So they really can provide a very detailed impact of temperature changes, especially with regard to land use models, for example, how it affects crop yields. And these models provide much more detail on technologies. So they usually provide a very rich technology mix on how the energy sector or the land use sector can mitigate and adapt to climate change, and what kind of impacts you will expect, but not only on emissions and costs, but also on any other land use or sustainability indicators like biodiversity, for example. So this is very rich, but what they do not provide is interaction with other sectors usually. You usually couple a few sectors like land use and the energy sector, but you hardly ever combine all economic sectors, which does happen here in the macroeconomic model. So both have disadvantages and advantages, and what they have in their objective functions, usually they minimize costs. Some of them also maximize welfare in a partial equilibrium model, so just for the sector, but they don't really have a utility function like they do in the macroeconomic model. So most of them just basically minimize costs. And from this, I think that these methods are also accompanied by different viewpoints. You have, on the one hand side, positive economics, which basically is positive here means it really just tries to look at empirical evidence, like positive science. So these are usually econometric studies. No, econometric studies are based on economic theory, but they still try to test those theories based on empirical data. So it's theory-based, but empirically founded. And in my point of view, process-based AEMS are rather like this. They're somewhat in between positive economics and, that's the other viewpoint, normative economics. They still make strong assumptions, which can be criticized, like that farmers and electricity providers are pure homo economicus. They have perfect or myopic foresight and much more. And on the other hand, you have normative economics, which really is what the top-down integrated assessment models are, because they really make a value judgment and tell you what maximizes social welfare. And that can be problematic because if you look at what's best for society, it doesn't necessarily have to be just the utility of everyone. It could be that raising the utility of the person with the lowest income has a much higher utility than raising income of a high person. So just how you formulate the utility function already involves some kind of value judgment. But that's the heart of the top-down macroeconomic model. So in the next slides, I will try to show you how people try to estimate the cost of climate change and show you how big the range of uncertainty is in this discipline. Before we move forward, we really have to distinguish between the costs, because I think that can be quite confusing because you can analyze a lot of costs of climate change. First, you have the costs of damages. So that's the negative impact of climate change on the economy and our society. In rare cases, you will have in the short and midterm opportunities. In the long term, I think opportunities will be very scarce. Then you also have the costs of adaptation, and you have the costs of mitigation. So those are like three types of costs that are very important in climate change economics. How do you actually estimate the cost of climate change? One straightforward way to estimate the cost is to first, of course, try to find out what are the physical impacts of climate change and or what can be attributed to climate change. That's a science of its own. And then you have the challenge of actually monetarize those impacts. So impacts on human health, ecosystem services, destroyed infrastructure, and so on. So that's a quite already challenging task, and it comes with a lot of uncertainties. Then, since a few decades, people try to do it also statistically, trying to find if there is some kind of correlation or causation between weather variation and economic output or economic growth. This is kind of disputed because people argue that weather variation is not equal to climate change, but I'm not an expert on this, so I'm not the one to judge. What you can also do, and this is what happens in top-down integrated assessment models, is you assume a damage function, mostly arbitrary. These hardly have any empirical foundations and theoretical foundations because we don't know what the impact of increasing temperatures on a climate scale does to the economy. But such things can actually provide you with a Nobel Prize because this is exactly what Nordhaus did. He assumed a damage function which looks like this. So that's the loss of GDP as a factor of temperatures. And it's more or less an exponential function. So it's kind of if you have to draw it, it would look like this going down. Yeah. So on the x-axis, you have temperature, and here you have the loss in GDP. Yeah. So here you would have 1, and here GDP would be 0, and this would be the increase in temperatures. This is what it would look like. Yeah. So it's a nice way to integrate temperature effects into economic models, but it's a very simple one, and it doesn't come with a lot of empirical and theoretical foundations. And no matter how you obtain those costs, they can usually be fed into an IEM, top-down IEM. It doesn't have to be a damage function. You can also do it starting from a physical impact point of view, which is what Nicholas Stern did for his famous climate report. Yeah, and this now brings me to two important concepts that we will now look into more detail. The one is the social cost of carbon, which relates to the marginal costs of greenhouse gas emissions. And marginal always means a minimal change in something, an infinitesimal change, actually, in mathematical terms. And you can phrase it like this. So the increase in the net present value of damages from now until the future, they usually assume a time horizon of 100 years, although CO2 stays much longer in the atmosphere, caused by today's emission of one more additional unit of carbon, usually measured in 1 ton of CO2. So you have to assume you now emit 1 more ton of CO2, and then you have to take into account the damage this additional ton does over its lifespan in the atmosphere. And then you have to discount the value because it's a net present value because damages take place in the future to come up with a figure for that. Right. I go into more detail in the next slides. And there's a counterpart to the social cost of carbon, which is the marginal abatement costs of carbon. So again, that's a change in abatement technologies. So you can say it's the increase in mitigation costs if 1 more additional unit of carbon, and that's usually 1 ton of CO2, is abated. And that, of course, highly depends on the technology that is employed. The methods that I introduced earlier approach this differently. For example, the top-down integrated assessment models, what they do is they really try to optimize welfare by finding the point where the social cost of carbon equals the marginal abatement costs, right? Because that's a point where you really minimize costs to society. And that's optimal from a welfare point of view, at least theoretically. And bottom-up AEMS are different because they actually do not use the social cost of carbon. They actually produce a marginal abatement cost curve as their output, right? And this makes them tools to actually identify an optimal employment of mitigation technologies to reach a certain climate target. And that's a crucial difference between those two methods. So I've already told you how you can calculate total cost of climate change and the various approaches to it, but I haven't actually told you yet how you can derive the social cost of carbon. Because it's a marginal cost, actually almost all calculations are based on models. And what you usually do is you take a top-down integrated assessment model and you run it for a business as usual scenario, and then you shock the model with one more additional unit of greenhouse gas or CO2. And then you estimate what this additional unit does, what kind of damages it does to the economy over the lifespan you consider of the CO2 molecule, more or less. And that means it's based on many, many assumptions. That includes the damage function I introduced by Mathias. More importantly, and this is what I will talk about in the next slide, the discount rate, so how much value you actually attribute to future impacts. And also the climate sensitivity, this relates to the simplified climate model in integrated assessment models, so how temperature reacts to changes in CO2 concentrations. And then you have a few others like your basic run, like projections of CO2 emissions, economic, demographic development, because your base run itself also determines how much one more additional unit results in damages. And then you also have different regional impacts, and then there's the issue of how you aggregate them. So there's a lot, but those three, the damage function, the discount rate, and the climate sensitivity, are the major sources of uncertainty in estimating the costs of the social cost of carbon. And the discount rate is very essential. The discount rate itself that is used in top-down integrated assessment models was first introduced by Ramsey in 1928, and it consists of three parameters, more or less. You have eta, which is the elasticity of marginal utility of consumption. You have G, which is growth in consumption, and you have delta, which is the pure time reference. So this first term, eta times G, actually makes sense, because what you do is you value an additional unit of consumption less than the first one. That actually accounts for, so if you have economic growth, one more dollar is less worth than the previous dollar, which makes sense. You have the famous example of a cake. The first piece of cake tastes really good. The second one is still good, but it's not as good as the first. And the fifth piece of cake might actually be really bad for you. So that's a very sensible approach to actually discount economic growth and wealth, because utility is decreasing. The other one, that's the one where you really have to make an ethical and normative judgment, because that's really the pure time preference, saying how much is, well, a healthy life of a future generation worth to us. And this is where many economists disagree on what this value should be. What's very interesting is that Ramsey himself said that there is no ethical argument that would allow this value to be higher than zero. He still introduced it, and people more or less abuse it still, although he himself said it shouldn't be higher than zero, because there's no way you can actually make the life of future generations worth less. Yeah, there was a big discussion about the discount rate when the Stern review came out in 2006. So that was one of the first major economic assessments of climate change. And it was put in context to Nordhaus, who would later win the Nobel Prize. And both of them employed integrated assessment models at the same time. But they did a few things differently. First was Nordhaus used a damage function, whereas Stern actually monitorized physical impacts. And one of the biggest differences actually was the use of the discount rate. So Stern really put the delta value, so they put time reference almost to zero. I think he put it at 0.1%, arguing that at some point we will be extinct, and that's reflected in putting at least some value into it. Whereas in Nordhaus, I think it was about 4%. And the effective discount rate was 1.4% in the Stern review and 5% in Nordhaus. And in the values they provided are different, substantially different. In Nordhaus, the value was about $10 to $15 per ton carbon, and the Stern review had a value of $85 per ton carbon. And that meant that according to the Stern review, it was really worth to start employing mitigation technologies, whereas Nordhaus would call for caution and not too much because it's not really worth it, right? And that really put a brake on how ambitious politicians were back at the time. So this is, although Nordhaus can be credited by putting climate change, highlighting it as an issue for climate change, because he was really one of the first to consider it as an issue. He's still, the way he provided his figures actually was a hindrance to motivate politicians to really make an effort in mitigating climate change. So that's one of the things he didn't do us any favor with, I think. Yeah, and this slide here shows you a short bandwidth of current estimations of the social cost of carbon. It actually just shows you the uncertainty with regard to the discount rate, disregarding other uncertainties. And here you can see that the impact of the discount rate really has a huge effect. So you can see here one of the latest publications by Nordhaus. It ranges between $20 and $200. So having a discount rate of 1% or 5% makes a tenfold difference in the social cost of carbon. That's a huge levering point, right? So if you're a politician like Trump, you can actually just, if you set the discount rate on whatever you like, it makes a huge difference. Yeah, and you can also see that between the publications, the values range a lot from 640 to 417. But that's even disregarding regional differences. I mean, if you look at Rick et al., which really tried to calculate social cost of carbon at a regional level, they have a bandwidth of, just for one kind of effective discount rate, for 2%, from $170 to $805 per ton CO2. So there are huge uncertainties, and it really depends on a value judgment on how big they are, right? As a comparison, these are a marginal abatement cost curve, marginal abatement cost values, and this is something that is now employed widely in the IPCC reports. So what they do not rely on top-down macroeconomic models anymore, but they really employ these bottom-up models to find mitigation pathways at least cost. And what you can see here, that you still have a lot of uncertainty, but that already here includes model and scenario uncertainty. So these values already include much more uncertainty than the slide before. So you can say that these values are much more robust than the social cost of carbon, although they still come with a lot of uncertainty, but they're much better guidance for climate policy than the social cost of carbon. And if you compare them, you actually will see that even the max values are below most social cost of carbon values. So it really seems like mitigation is really worth the effort. Just simply from an economic point of view, which I think can be criticized as well, looking at the existential threat that climate change poses. So given these limitations and flaws of the social cost of carbon, one has to ask him or herself, are top-down AEMS totally useless? And there are some scientists who now say yes. I wouldn't fully agree with them, but they have very good arguments because they point to three major flaws, which I already mentioned. And the one is that inputs and damage function are often arbitrary, right? So you have the discount rate, which reflects some kind of social value of the modeler, implicitly or explicitly. The damage function, which still is rather arbitrary. They now try to find empirical data for it through weather variation statistical analysis, but that's disputed as well. And you don't know anything about the functional form because you can test many functional forms and some of them might fit better than the other ones, but you never will know which one's the best, right? And that's also important. There's no consideration of what Weizmann titled fat tails. That means low probability, high risk events. And this is what you just have to think about the tipping points, right? There's really, even if there's a low probability of a high risk event, the risk is actually really high because you have to multiply those two values. And coming from a risk approach, that really those models usually fail to account for that and underestimate the potential social cost of carbon. Yeah, and then you also have the uncertainties in climate sensitivity, which is still an issue to be resolved in natural sciences. My personal judgment on this issue is that you have to be really careful when you're presented with results from top-down AEMS. And these results should not be interpreted as facts, especially not social cost of carbon estimations. However, I think there's some usefulness in them because they can be used as pedagogical devices. Because they can tell you a lot about interactions between different sectors. They can tell you a lot about dynamic effects of impacts on capital accumulation and consumption issues, which you don't see in bottom-up process IEM. So you need this top-down point of view is something that you need to get a feeling about the interactions. And there's also a useful argument. You can say that even these stylized models argue now for the need to tackle climate change immediately and very ambitiously. So the times when models provided very low values are actually gone, unless you put in really high discount rates. But, and this I have to say again at the end, there is a real world politics danger in using social costs of carbon estimates because they are already used for policy decisions. There's a link to a nice article on Carbon Brief which shows how it has been used and misused in by US politics, because the Environmental Protection Agency still runs to this date top-down integrated assessment models developed by Nordhaus. And politicians are more or less free to determine the discount rate values in these models. So they can, whatever value they like to have, they can have it. And I think that's a very arbitrary approach to tackling climate change and a very dangerous one. We even were approached a team of climate change economists in Austria, which I was part of. We were approached by the Ministry for Climate in Austria, trying to find some recommendations on what values to use. And I think almost everyone in this group agreed that the social cost of carbon should not be used as a guidance, but we should rather rely on estimates by bottom-up integrated assessment models, which provide you with target-based values. So they provide you with a marginal abatement cost curve and how to reach it, and at an agreed target at least cost. This is something that's much more important. So you have to keep in mind that integrated assessment models have become very diverse and that these bottom-up process-based models are really gaining momentum. They are widely used now in the IPCC assessments, and they're really good tools to find cost-efficient technical solutions. They rest on fewer assumptions, especially ethical assumptions, but they still have plenty, though. So you shouldn't also take these values at face value, but they're much more robust and practical for policy decision making. And at the end, we will need macroeconomic models to try to model the interaction between sectors. So what's really on the agenda right now is try to integrate both types of models, right? And that's important, and that's something that we will talk about and highlight in the AEMS, is that everything here is still a very, very technical point of view, and we will need just much more than just technical solutions. So that's at best what even the bottom-up process-based models can provide, is like a bottom baseline on where to go, but we will need much more effort and really social ecological transformations to really tackle climate change. So we really need also changes in values and norms. And I think we will have some very interesting lectures on that to come. Yeah, so at the end, a few more words on COVID-19 and climate change economics. There's a pessimistic view, which say that, well, everything will bounce back to business as usual pretty quick, which seems to be the case for CO2 emissions in China currently. This graph here from Carbon Brief really shows that while they decreased substantially in February, they really bounced back in May and are now actually higher compared to 2019's level in May. So this is something that people might be right about. There's also the danger that people might care less about climate change mitigation if they're faced with a recession and loss of income and are basically in a dire situation. And also the rising nationalism that comes with closing borders might make international coordination, which is already very burdensome, even more problematic. Yeah, but there's also the optimistic view, which means that, well, green investments are actually a win-win option, which which a survey of leading economists has shown. Also, the European Commission really, at least rhetorically, said that it really wants to strengthen the Just Transition Fund and push for rather green, not fully green, but rather green recovery program. And there have been surveys in Germany and Austria that show that people still worry more about climate change than COVID-19. Still, at least. So that's the optimistic view. I guess, as always, it will be somewhere between those two. And I don't really know where it goes. I just hope that it rather follows the optimistic view than the pessimistic view. So there are a few take-home messages for you. Regarding climate change, I hope I made it clear, and Helge will make it much more clear. We are currently experiencing unprecedented changes, which are driven by human economic activity. And the current trajectory poses existential risk, so it's really imperative to stay below 1.5 degrees. A lot of reasons for that. And that makes it also an issue for economics. And economics assessment have many drawbacks, which I hopefully was able to show. So they contain value judgments, a lot of uncertainties, unknown unknowns, so things that we don't even know we don't know. But they still provide some useful information. So they can tell us something about economic dynamics. They can at least show us technical solutions, so viable and efficient mitigation of models. Which something I couldn't talk about is they can also show how you can design policies to be more socially acceptable and more equitable, so that low income households are not hurt as much as rich households when it comes to climate policies. And even the most crude assessments conclude, well, mitigation is the best adaptation option, and it's also the best growth option if you aim for economic growth. And taking action now is less costly than later. And finally, climate change and economics. This is something that we will talk a lot about in AEMS, is that tackling climate change will require a major transformation of our economic and social systems. So, and we're in the midst of deciding what we want and how we want to get there. So value judgments are always involved, but these judgments should be left to policy decision-making and societal decision-making and not modelers, I think. Because we as modelers and scientists, we can only provide options, but the decision should be made by policymakers and society. That's at least my point of view. Yeah, and COVID-19 provides both an opportunity and a threat, and it's up to us to decide what we want it to be. Okay, so thanks for listening, and I'm looking forward to a vivid discussion. I was only able to really talk about brief aspects. It's not a very comprehensive assessment, I think, of climate change economics, but I hopefully was able to dive into very important aspects. And see you soon.